All right, in this video, I want to find and classify all critical points of this function over here. So the critical points can be classified as maximums, minimums, or saddle points. So the first thing I want to do is I just want to find the critical points. In order to find the critical points, I need to derive the equation in terms of x. So I'll call that f of x over here. That means I'm deriving this equation in terms of x, and I'm treating y as a constant. So let me derive this. The derivation of this first term here is just negative 2x. The derivation of 4y squared is just 0 because I'm pretending like y is a constant, so this is going to disappear. The derivation of negative 4xy is just minus 4y because the derivation of x is 1. Then the derivation of 4x is just 4. Then I want to derive this equation with respect to y. So over here, if I derive with respect to y, I'm pretending like x is a constant. So this first term is just going to become 0 if you derive a constant that's 0. This is going to become 8y. This is just going to become minus 4x because derivation of y is 1 times a constant. It's just a constant that stays. And the derivation of 4x is just 0 because, again, we're pretending like this is a constant. Once I've derived these two, I just want to make them equal to 0 and solve them. Now, sometimes you can solve them individually to get multiple critical points, but in this case, we are going to have to use substitution because we have two variables in each equation. So I need to solve this with substitution to find my critical point. I'm going to isolate the 2x over here. I feel like it's the easiest variable for me to isolate. Or even the x in this one is pretty easy as well. Doesn't really matter. I'll just isolate this over here. So 2x equals negative 4y plus 4, and then divide everything by 2. So x equals negative 2y plus 2. And I'll substitute this into this equation and solve for y. That'll be plus another 8y plus another 8. I'll move the 8 to this side and I'll combine these two like terms. So negative 8 equals 16y and then divide by 16 on both sides. So negative 0.5 or negative 1 over 2 equals to y, whichever one is fine. I'll sub that in here to find my x. So x equals to negative 2 times negative 0.5 plus 2. Negative 2 times negative 0.5 is, oh, I made a mistake here. This is minus 8, not plus 8. Means this is positive 8. This is positive 0.5, making this positive 0.5. So that negative 2 times 0.5 is negative 1 plus 2, which means my x is just 1. So in this solution, I have one critical point, which is 1, comma 0.5. Now, in order to classify this critical point as a maximum, minimum, or a saddle point, I need to find something called the Hessian, which is derived from the Hessian matrix. I'm going to explain that over here. We have three cases for the Hessian. The first case is if h, which is your Hessian, I'll explain how to calculate that in a second. If h is greater than 0, and fxx, which we're going to find as well in a second, is also greater than 0, this means we have a local maximum. If h is greater than 0 and fxx is less than 0, oh, sorry, this is a local minimum, not a maximum. local min, this is a local max. And if h is less than 0, it's just going to be a saddle point. So this is how we classify our critical points for a function like this. So now I'll just explain what h is. H is just derived from the Hessian matrix. The formula for h is just fxx times fyy minus f squared of xy. All we have to do is we have to calculate this, we have to calculate fxx, we have to calculate fyy, we have to also calculate fxy, and then we just put it in this equation, and then that will classify this saddle point for us. So let's start with calculating fxx. To find fxx, I just go to my fx equation and I derive it one more time with respect to x. So these two are just going to be constants and disappear, which means I'm just left with the derivation of this negative 2x, which is negative 2. Then I'll find fyy, which is deriving this equation a second time with respect to y. Derivation of 8y is 8, and derivation of negative 4x is just 0 because we're pretending like x is a constant. And last, I'll find fxy. Fxy, you can derive the first equation with respect to y or the second equation with respect to x. Doesn't matter, you'll get the same answer for both. For example, if I derive this with respect to y, this is going to disappear, this is going to disappear, and we just have the derivation of negative 4y, which is negative 4. And if I did it over here and I derive this with respect to x, this will just disappear, and we're just left with the derivation of this, which is negative 4. So it doesn't matter which way you do it. Now we want to sub these values into our Hessian equation. So h equals fxx times fyy minus fxy squared. I'm going to calculate this. So this is negative 16 minus 16, which is negative 32. So now I'm going to compare all of these to my solutions here. If h is less than 0, it's automatically a saddle point. If h would have been greater than 0, then I would have looked at my fxx to classify as a minimum or a maximum. So in this case, the critical point here is a saddle point because h is less than 0. Now, before I end this video, I'm going to quickly talk about something else really quick. So I'm going to share my screen here. And in 2023, I've uploaded, so I just got this recently on YouTube. I uploaded 257 videos and I only got 218 new subscribers, which obviously I'm grateful for. But I'm hoping that I can get these numbers to become even one day. So I'm going to put a counter at the end of my videos from now on. I'm going to try and see whether my new subscribers can catch up to my new uploads, basically from like January 1st of 2023. So I'm going to add that to the end of all my videos. Basically, I'm just going to put a little counter there, comparing the number of uploads versus the number of new subscribers from January 1st, 2023. So if you made it to the end of this video, you thought it was useful, please hit that like button and subscribe button. It really helps me and it helps the channel. Thank you.